Theovis, the idea made visual.
Blurring a photo, the echo in a cathedral, smoothing noisy data, even adding two random numbers. Underneath, they're all the same operation. It's called convolution.
I've computed convolutions and never had any feel for them. The formula is this tangle of flipping and sliding and integrating. What is it actually doing?
By the end, it'll feel like one simple motion. Slide one thing across another and tally the overlap. Here it is in all its forbidding glory. Don't panic. Every symbol corresponds to one physical move. Flip the second function, slide it, multiply the two, and add up the result.
Flip, slide, multiply, add. 4 steps. Let me see them happen instead of just reading them.
The operation is older than its scary name. Back in the 1830s, Duhamel was already adding up a system's responses to a train of small pushes, the seed of convolution, long before signal processing existed.
So, engineers were quietly convolving a century before anyone drew the sliding picture. The idea kept being rediscovered because it's so fundamental.
Up top is a signal. 2 bumps. The little kernel slides across it. At each position, we multiply the 2 where they overlap, shade that product, and add it up into a single number.
And the bottom curve is that running total as the kernel slides. So the output at each spot is just how much do these 2 overlap right here.
Exactly. Convolution is overlap, measured continuously as one function glides past the other. On real data, the integral becomes a sum. The kernel is just a short list of weights, and you slide it along, at each step multiplying and adding the numbers underneath.
So a 3-number kernel, like a quarter, a half, a quarter, is a tiny weighted average that smooths as it slides. Convolution by hand is that simple.
Let's convolve by hand. Slide 1, 1 across 1, 2, 3. At each position, you add the overlapping products. First 1, then 1 plus 2, then 2 plus 3, then 3.
So the result is 1, 3, 5, 3. And the outputs sum to 12, which is 3 times 4, the product of the 2 input sums. A nice built-in check.
The one odd step is flipping G. There's a clean reason. In a physical system, the output now is built from inputs in the past. Flipping lines up each past input with how much it still contributes now.
So the flip is just bookkeeping for cause and effect. The most recent input weighted by the freshest part of the response. Got it.
Here's where convolution comes alive. Hit any stable system with a single sharp spike, a hand clap in a room, and it answers with a characteristic decaying response. That's its impulse response.
Like the way a single clap in a big hall spreads into a long, fading echo. That echo is the room's signature.
Picture the simplest room echo. The original sound plus a softer repeat a moment later. Convolving your voice with that produces one echo. Add hundreds of faint, spread out repeats, and you get rich reverberation.
So a reverb plugin literally convolves your track with a recording of a real hall's impulse response. You can borrow the sound of any cathedral.
Now, the trick: think of any input as a dense row of tiny spikes, each scaled by the signal's value. The system responds to every spike with a scaled, shifted copy of its impulse response.
And the total output is the sum of all those overlapping echoes, which is exactly the slide and add we just watched. So the system's whole behavior is one convolution.
So this is the grand statement of signal processing. Any linear, time-invariant system, a filter, a room, a circuit, does nothing but convolve your input with its impulse response.
So if I know how a system reacts to a single click, I know how it reacts to everything just by convolving. That's a stunning amount of power from one measurement.
There's even an identity element. Convolve any signal with a single perfect spike, and you get the signal back, untouched. The spike is the do-nothing of this world.
So the delta spike is to convolution what 1 is to multiplication. Convolution really is its own little algebra.
Now the applications pour out. Blur an image by convolving it with a little blob. Every sharp point gets smeared into that blob's shape, and the whole picture softens.
So a camera's out-of-focus blur is literally convolving the scene with a disk. The blur kernel is the shape of the smear.
For a photo, the kernel becomes a little square that slides both across and down the image, blending each pixel with its neighbors in 2 dimensions at once.
So the same idea just gains a dimension. A 3x3 grid of weights sweeping the whole picture. That's every filter in your phone's camera app.
Enough theory. Here's a real photograph, drowning in noise. Watch what one tiny blur kernel does. We slide this 3x3 box of equal weights across the image, replacing every pixel with the average of its neighbors.
And the grain just melts away. On the left, it's about 17 decibels of quality. On the right, after sliding that little averaging window, it's 23. A real measurable cleanup from one kernel.
Same flip, slide, multiply, add we started with. Now you can see it healing an actual image. Change the kernel, change the effect. A spread out kernel blurs. A kernel that subtracts neighbors finds edges. A short, flat kernel averages away noise.
So all of image filtering and audio effects is really just pick the right little kernel and slide it. One operation, endless tools.
Want the opposite of blur? Convolve with a kernel that compares each point to its neighbors. Flat regions cancel to 0, but sudden jumps light up. You've detected edges.
So smoothing and sharpening aren't opposite machines. They're the same machine with a different little kernel. That's beautifully economical.
Now swap the blur for a difference kernel, the Sobel kernel, on the very same photo. Instead of averaging neighbors, it subtracts them. Flat regions fade to nothing, but wherever the brightness jumps, the output lights up.
So the same sliding motion, with a kernel that subtracts instead of averages, traces every edge. Her collar, the glasses, the stars on the flag. One operation, opposite jobs.
Here's a jump that surprised me the first time. Add 2 independent random quantities, and the distribution of the sum is the convolution of their 2 distributions.
Wait, the same flip, slide, multiply, add from image blur shows up in probability? Why on earth would adding dice involve convolution?
Because to land on a given total, you sum the chances of every pair that adds to it. Low plus high, high plus low, and everything between. That weighted sum over all pairings is exactly a convolution.
So sliding one distribution across the other tallies all the ways to reach each sum. The overlap picture and the probability picture are the same picture.
Roll 2 dice. Each is flat, equally likely faces, but their sum peaks at 7 and tapers to the ends. A triangle. That triangle is 2 flat distributions convolved together.
So 7 is most common simply because it has the most pairings. The shape of luck is a convolution.
Back in one dimension, the humble moving average, replace each point with the average of a window around it, is just convolution with a flat kernel. It quietly cleans up jittery measurements.
So every smoothed stock chart or sensor trace is a convolution. The wider the window, the smoother the curve, and the more sluggish it reacts.
Now add more and more random pieces. Convolve a distribution with itself again and again, and almost any starting shape smooths toward the same bell curve.
So that's why the normal distribution is everywhere. Repeated convolution grinds every lumpy shape into the same smooth bell. The central limit theorem is convolution at work.
It also behaves beautifully. Convolution is commutative. F with G equals G with F. And associative, so you can chain filters in any grouping and get the same result.
So stacking a blur, then an edge detector, is itself just one combined kernel. The filters compose cleanly. That's why pipelines work.
And now, the deepest fact of all, the convolution theorem. Take the Fourier transform of a convolution, and the messy sliding turns into simple, pointwise multiplication.
So the hint from the Fourier episode pays off. Convolve in time, or just multiply in frequency. They're the same. That's an enormous shortcut.
Skip the flip, and the same slide and tally becomes correlation, a detector that peaks when a signal matches a template. It's how GPS locks onto a satellite's code, and how radar recognizes its own echo.
So convolution blurs and combines, and its unflipped twin searches and matches. The same motion, 2 superpowers.
This isn't only elegant, it's practical. A direct convolution is slow, but you can transform both signals, multiply, and transform back. And with the fast Fourier transform, that's dramatically quicker.
So big blurs and long filters are done in the frequency domain for speed. Cooley and Tukey's fast algorithm shows up here too.
Here's a sneaky one. When you multiply 2 numbers, or 2 polynomials, the digits, or coefficients, combine by convolution. Every pair contributes to each place value, with carries on top.
So grade school long multiplication is convolution in disguise, and that's why huge numbers are multiplied using the FFT. It loops back again.
One more giant. Convolutional neural networks slide small, learnable kernels across an image, each one hunting for a feature, an edge, a texture, an eye. Stack them, and the network learns to recognize the world.
So the same slide and tally that blurs a photo is what lets a network read handwriting and spot faces. The kernels are just learned instead of handpicked.
And if a known process blurred your data, you can sometimes undo it. Deconvolution. Knowing the kernel, you work backwards to sharpen what was smeared, the way telescopes clean up their images.
So convolution isn't a one-way street. With the kernel in hand, you can partly reverse the smearing. That's how blurry photos get rescued.
Let me gather it up. Convolution flips one function, slides it across another, and at each position tallies the overlap. That single motion is filtering, blurring, echoing, and adding random variables.
Exactly. It's how every linear system turns input into output, the way distributions add, and through the Fourier theorem, it's secretly just multiplication wearing a disguise. For the full treatment, impulse response, the convolution theorem, and the algebra, these lay it all out carefully. We've slid kernels across signals. Next, one special little kernel, comparing a point to the average of its neighbors, turns out to govern heat, waves, and fields, the Laplacian.
From convolution to the Laplacian. See you there.
If it finally clicked, subscribe. It really helps. And I'll see you in the next one.